Good morning. My name is Marin. This is my video submission of midterm 103 or midterm 2 from class MAE 103 fluid mechanics. So problem number 1 says the setup shown here provides a liquid flow through the tissue for a physiological experiment, taking readings for heights given and other geometrical information on the figure. Develop an expression for the storage rate of the liquid in the tissue. Keep in mind that the tissue leaks 1% the incoming flow. Let's see. As you can see, I set up my y and x coordinates, y pointing upwards, x to the right. Let's see, the assumptions I made were that it's a non-moving control volume, it's constant density, and it's uniform flow. And then a couple of the formulas that I used the conservation of mass for control volume formula, the uh, partial control volume rho d volume dt is equal to negative integral of the surface rho v dot n dA. And then also from my notes, I got that d volume dt is equal to the integral surface of v dot n dA. So I came to the conclusion that we're looking for d volume dt, and I hope I'm right. I don't know. To be honest with you, the control volume that I drew was solely around the tissue. The reason for this is we just wanted what's it called? We just wanted the tissue the volume dt of the tissue, so I didn't really need much more than that. The n vector is drawn out. I might have to change color because maybe it doesn't look as good as it should. Also there's V in and V out, and what's it called? We didn't have the initial the V the velocity of the incoming flow, so I had to use Bernoulli's equation between 2 points. Point 1 being at the tank, and point 2 being inside the pipe itself. And I found out that P1 is equal to P2, which is equal to P atmosphere. It's also equal to P3. It's not written here, but I did say it. So that's why I was able to get rid of P1 and P2. What's it called? What else? V1 is approximately 0, so I was able to get rid of that too. And then H2 was 0, so I was able to get rid of that too. The height at point 2 is 0. So then I got that V2 is equal to the square root of 2 rho 2g h1, which is equal to V3, the velocity at point 3, which is the outflow as well. Used the formula of conservation of mass, the partial integral control volume rho d volume is equal to I'm sorry about the noise is equal to negative integral of the surface rho v dot n dA. Pulled out the rho because it's a constant. We assumed constant density. Did we? Yeah. We assumed constant density, so we were able to pull that out. Here's where I'm a little confused. This is where I started getting confused. Well then, from the definition of d volume dt, I got that d volume dt is equal to the partial derivative of the integral of the control volume rho d volume partial t all over the negative density. But I wasn't sure if I was going in the right way, so I tried another method. So I recall that the volume dt is also equal to q, which is equal to, you'll see it there or whatever. It's equal to a1 plus a2 plus a3, each being an outlet or whatever, an inlet and an outlet and an outlet. So what's it called? So then from there, I recalled that all of that is equal to negative q in plus q out. And that q is equal to the velocity of the flow times the area, the cross-sectional area. Q2 was A2 V2, but also that the flow at the pipe was also the same at the flow at point 1, flow from tank, the flow from the tank. So what's it called? So I said that Q2 is equal to Q1 is equal to A1 V1. But I needed the area first, so I did some of the work down here for the area. Some of the unknowns, just used trigonometry to find them, and this is where I got to. It was like 12 in the. It was like midnight, and I didn't have any more ideas, so I just moved on. Problem number 2. Water accelerated by a nozzle to 35 meters per second strikes the vertical back surface of a cart moving horizontally at a constant velocity of 10 meters per second in flow direction. The mass flow rate of water through the stationary nozzle is 20 kilograms per second. After the strike, the water stream splatters off in all directions in the plane of the back force. A. Determine the force that needs to be applied by the brakes of the car to prevent it from accelerating. What is the force needed if the back of the car has 450-degree angle and all of the jet to that direction, and the jet goes in that direction? Assume the mass of the water that wets the back surface is negligible. So for part A, the assumptions I made: a moving control volume, the mass of the water that wets the back surface is negligible. Therefore, the sum of m dot out is equal to 0. That's what I'm thinking. I went with it. I'm hoping I'm right. 3, steady moving control volume. 4, assume the mass of the water. It's the same. 4 and 2 are the same, actually. I didn't notice that till now. So I had Vj is equal to 35 meters per second. The velocity of the block is equal to 10 meters per second. I thought it was a block. It turned out to be a car. The m dot j is equal to 20 kilograms per second. I drew my control volume to surround the block, and drew my n pointing out, and what's it called? Conservation of mass for a moving control volume. I used that formula, which was rho. It's the partial derivative of the integral of the control volume rho d volume partial t is equal to negative integral of the surface rho w, because it's moving, dot n dA. W is your relative velocity, so it's Vj minus the velocity of the block, which is 35 meters per second minus 10 meters per second gives us 25 meters per second. Then I got the partial of the mass of the control volume dt is equal to m dot in minus m dot out, and then m dot out cancel out because of the assumption number 4. And then what's it called? Partial m the partial of the mass control volume dt or whatever is equal to m dot in. Then I used the ratio to try and find m dot in, and I found that m dot in over w is equal to m dot j over the velocity of the jet, and then I got m dot in is equal to w over the velocity of the jet times m dot j, which gave me 25 over 35 times 30, 21.43, rounded to two significant figures, kilograms per second. Then I recalled, I used the momentum equation the sum of the forces is equal to, and I suck at reading this, but the first term, the integral of the control volume rho v dot volume goes to 0 because it's steady, which leaves us with the second term. And I broke up the second term even more, which gave me the sum of the forces is equal to negative m dot n vn, the velocity, times the velocity, plus m dot out times the velocity of the out or whatever. And then using assumption 4, m dot out is 0, so I was able to just narrow it down to the sum of the forces is equal to negative m dot n times w. W being our relative velocity, and I got negative 535.71 newtons as the force that the brake would need. Now for part B, I went through the same process up to the momentum equation, so I didn't really write it down. But then when it came to the momentum equation, I found this is where I was having difficulty, and I just guessed because I didn't have any other idea. Same process. The integral control volume rho velocity d volume goes to 0 because it's steady. But now when we break this, and then we break this up, and the m dot out is cancelled because of assumption 4. But now the velocity that's going inside the control volume is w plus w cosine of 45. I'm not really sure how I got that. I just guessed. Cause I could have used sine or cosine. I was just trying to think of like as a vector, but I'm not sure if that's a correct way of thinking of it. I don't think it is, cause it's a velocity, not a force. But whatever. It was the best I could come up with. And so the sum of the forces is equal to negative m dot n vn, and then I just plug in numbers. Negative the sum of the forces in the x direction is equal to negative 21.43 kilograms per second times 25 meters per second times 1 plus all in parentheses 1 plus cosine of 45 degrees, which gave me a braking force of negative 914.58 kilogram meters per second squared, or negative 915 newtons. Yep, and that's my test. So yeah, thank you very much.